A special case in projectile motion is zero launch angle, which means theta. Let me just go over the graph. Here is an object launched with an initial velocity in this direction and a length somewhere in here. This is called the range, which is x, and this is the height. I marked 3 points, point number 1, 2, and 3. At point number 1, the initial velocity, and that's usually given. The initial velocity is a vector which consists of velocity in the x direction and velocity in the y direction. Velocity in the y direction is 0. Consequently, velocity in the x direction equals initial velocity. The coordinates of point 1, this is point 1 here, the coordinates for point 1 will be 0 for x and h for y, which is the height. Point number 2 is the origin, which means this is the y-axis and this is the x-axis. And this point here is 0 for y and 0 for x. So the coordinates at this point is 0 and 0. Point 3, the coordinates at point 3 would be x for the x direction, which is the range, and 0 for y. Let's try to drive the equations of motion for this special case. X would equal x initial plus the initial velocity of x times time plus 1/2 acceleration times time squared. Since there is no acceleration in the x direction, a of x equals 0, this term equals 0. And the initial displacement for x is 0 since it starts right here. That's a 0 point. This term is 0. So x equals initial velocity of x, which happens to be the initial velocity altogether, because initial velocity in the x direction equals the initial velocity cosine theta, which is 0, and cosine theta equals 1. So initial velocity equals the initial velocity of x. X equals initial velocity times time. And if you look close at this, you know this equation. That's the same equation as speed. Our next equation would be y. Y equals y initial plus initial velocity of y times t minus 1/2 the acceleration. And it's minus because the motion is going downwards. And the acceleration is the acceleration of gravity times t squared. Y is 0 here. So this is 0 equals the initial value for y equals h plus the initial velocity in the y direction is 0, so this whole term becomes 0 minus 1/2 gt squared. This is a good equation to figure out time. 0 equals h minus 1/2 gt squared, and t squared would equal 2h over g. Time would equal the square root of 2h over g. Now if you need to figure the velocity in the y direction, because as we move in the graph, as we move here, there will be a velocity here in the x direction and a velocity in the y direction. Velocity in the y direction is going to be negative since it's being pulled by gravity. The velocity for y would be the y would equal the initial of y plus the acceleration times time. This would equal the v initial is 0 and the acceleration equals negative g. Velocity in the y direction equal negative g times t. Now one more item we need to add to this is the x here, which is the range, which is x would equal, and if you go back here, x was initial velocity times time. So that would be initial velocity times time, and we know what time is. Time is right here. So initial velocity times the square root 2h over g. Let's try this example with numbers. Let's say we have an initial velocity of 16 meters per second and a height of 8 meters. Let's find out range. So maximum height obviously is going to be 8 meters, because that's as high as it's going to get. If the second it leaves, gravity starts to pull it and it's going to slow down. So we know the maximum height. Let's say we need to know velocity here, a split second before the object hits the ground. Now the range is x, the initial, which happens to be 16, square root of 2 times the height, which is 8, divided by gravity, which is 9.81. And that would equal 16. Let's see what that square root is. And the range is 20 meters, 0.43. 20.43 meters. The velocity here is the velocity in the x plus the velocity in the y. And the velocity in the x is v initial, so velocity would equal v initial plus velocity in the y. Now the magnitude for velocity initial is known as 16 meters per second, and that's the same as the velocity in the x direction here, which is this one here. That's 16. But we need to know the velocity in the y direction here. And velocity in the y direction was negative g times h. So velocity in the y direction equals negative g times h, which is negative 9.81 times 8 meters. And that would be 78.5 meters per second. This is how your velocity vector at this point looks like. Velocity is 16 in the x direction minus 78.5 in the y direction. The magnitude of velocity at the landing point would equal the square root of 16 squared plus negative 78.5 squared. And we do need the calculator for that. 80.09 meter per second. Let's also find the landing angle. Right here. Now, you have, let's draw the vector here. Now we have the x this way, and we have the y going this way, but doing it head to tail would be this way. The resultant vector is right here. We need this angle. This is 80. From trigonometry, since we have all three numbers, we could use sine, cosine, or tangent. Now, if you were to use cosine for this angle, that would be 16 over 80 inverse cosine. If you were to use sine, that would be negative 78.5 divided by 80 inverse sine. And if you were to use tangent, it would be negative 78.5 divided by 16 inverse tan. Any one of those will give you this angle, a square. For the inverse sine, it's 16 divided by 80.05. Inverse sine, inverse cosine, and the angle is 78.47. Try inverse tan, 78.5, and negative divided by 16 equals inverse tan. Also 78.47, which is very close to this one. Equals. Here's a brain tickler. When we studied the zero launch angle projectile problem, which starts at the maximum vertical distance, we called it y max or h. You might wonder how the symmetry property of the projectile path pertains to the zero angle case. If you are not familiar with the symmetry property of the projectile motion parabolic path, watch my first video on projectile motion. Well, if you did wonder, the answer is yes, the symmetry holds here too. When we studied the zero launch angle motion, we covered half of the path. How can we use this information? The final velocity vector right before the object hits the ground, Vf final equals Vx final, also a vector, plus Vy final. We need to know the initial vector. If we were to launch the object at this point, since it's symmetric, it should resemble it somehow. Let's copy and paste this vector and see how we can make it fit here. Paste. It looks like it has to be flipped vertically. Let's rotate it vertically and it would fit right here. It looks like we have few changes. There is no changes in the x direction, which means velocity in the x direction equals the final velocity in the x direction. The initial velocity in the y direction seems to have changed sign. Final velocity in the y direction equals negative the initial velocity in the y direction. Last but not least, initial theta also change signs equals negative final theta. I hope you enjoyed this tutorial and I hope to see you in my next video.